So this time, we're going to approach this whole interpolation problem again, and we're going to make it faster, and we're going to do it for the Gaussian RBF. So in the series of lectures that we've been putting together for MATLAB, we've been going through building up a nice bit of code for, say, RBF interpolation, or kernel interpolation more generally. And so we started off with just showing how to do it for one dimension, then we expanded it to 2 dimensions, and then we did an approximation of Franke's function, which is a standard benchmark. And we did that for both the Gaussian RBF and also the exponential dot product kernel. And then in the next lecture, I showed you how to code up the exponential dot product kernel much faster. And we saw a 10-fold increase, or even a 100-fold increase from using for loops. And so it's a little bit more complicated to do with the Gaussian RBF. Sorry, I just ate lunch. And I'm going to show you how you can do this. And it isn't too different, but there's two little matrices you need to make in addition to what you usually make for the Gaussian, or for the exponential dot product kernel. So why don't we go ahead and talk about that a little bit. So remember here, the problem that we're trying to resolve is this. We have a function that we don't know, but we have samples. So we have the samples f of this function at the sample points xi. We want to be able to create an interpolation of xi, and that is this function s. And s is supposed to match up exactly with f at all these interpolation sites. And what that leads to is it leads to this linear equation where you have this matrix of kernel functions, which we call the gram matrix, multiplied by the weights that are in our interpolant, and that should be equal to this vector of samples, or the outputs of our samples. Now, something that's important to note is that you get this matrix by evaluating s at x1, x2, x3, etc. And then you can pull out these kernel functions as a row vector and multiply, and the weights become a column vector, and then you just build this matrix up one at a time for each I, and that's how you make this. You can also think of this as projecting a function f in a Hilbert space, reproducing kernel Hilbert space that corresponds to this kernel, onto the span of these particular kernels centered at the sample sites. So last time what we did is we exploited an idea where we could take a matrix of our sample sites, xi, and if we take their matrix, where you take x transpose times x, then you get a whole matrix of pairwise dot products of your sample sites. And after that, all we need to do is throw it into the exponential function, and then it gets exponentiated inside of MATLAB entry-wise. And that gave us the gram matrix for the exponential dot product kernel with almost no effort. So that required no loops or anything else like that. But when we talk about the the Gaussian RBF, it is a little bit more complicated. We don't just have x transpose y inside of our function, our kernel function. What we have is x minus xi minus xj, and the norm of that squared. And so we need to come up with a way of doing that. And so here with the Gaussian, we have the exponential, this is exponentiated one at a time, and what we can do is we can go ahead and pull that out. Oops, did not mean to move myself. Let's see. And we can go ahead and pull out the exponential, and we can pull out the -1 over mu. And so we're left with this general matrix that we need to do where we're taking the pairwise distances between each of our sample sites and then squaring them. And if we can make this matrix, then we can actually do this for every RBF. And so that's good motivation to try to do this, and it will make all of our code much, much faster. And so what we need to do next is we need to do this. And so we take all these pairwise distances and we write them out as an inner product, or a dot product between, say, x minus j against x minus j. And then you can go ahead and expand that. And so then here on the left of each one of these blue entries, we have, say, x1 going down to xm for that first bit. And so then, and all of those are just the norm squared of all those. And then if we take a look at the middle term, we get xi transpose times xj, which is just dot product between them. And by the way, that's exactly what you got from this guy. And so we can throw this one into the middle, just multiply it by -2. And then you need to do the same with the right-hand side. And so what we need to do is we need to find some way to get the xi magnitude squared. And the way you do that is you take this matrix and you just take its diagonal, and then you use repmat to repeat that matrix from the diagonal. So it's basically a vector you get out of it, and you're just going to repeat it straight down one row at a time and make multiple copies. And then you're going to have that as one of the matrices that you're making out of these components. And then the last component is just that same matrix but transposed. And so once we do that, then that'll give us a fast way of doing this algorithm. So with all that said, why don't we go ahead and jump into it. Okay, so here I went back to the same MATLAB code that we had a little bit ago, and so this was about 2 lectures ago that we did this, and I'm basically going to go through and, just like we did last time, find all the spots where we were doing the stuff with the kernel functions. So that would be here, the double for loops. So just to walk you through the code again, in case you forgot, we are going to be interpolating Frankie's function, and if I go ahead and plot this, I'm going to show you the Frankie's function, and let me just go show you all at once the sample sites as well. So here we go. This is Frankie's function with the sites that we want to sample. So all the little blue plus signs on here are our sample points, and you can see that they're distributed around. I think we have 100 samples if I look at the code right now. Yeah. So we have this here, how many samples, and that tells us how many samples we have. Again, we're generating this with the Halton sequence code. This code is a little bit deprecated. There is a proper MATLAB command now for Halton sequence, but when I started doing this stuff, it was before that was made, so I still have this floating around, and I happen to forget to install the new toolbox for statistics. So I'm using this. It's fine. It's the same sort of thing. It basically is semi-random points, and so it saves you the trouble of having to make a grid of sample sites, and it's maybe a little bit more natural to interpolation anyway, because you're not always going to have exactly interpolated sites at your mesh. Okay, so essentially, yeah, that's our function, and that's what we're sampling. And so this H is going to be what all our samples, and that's more or less the X matrix that I was talking about before. And so now here, it looks like we didn't comment out the exponential dot product kernel, and I'm just going to get rid of it altogether. And because this is going to be code specially made for the Gaussian RBF. And in fact, we're not really going to use this necessarily, but I'll keep it around just in case. Okay, so again, let's go ahead and do a tick and a talk to measure the time it takes to run this for loop. And so if we go ahead and run it, it takes 0.05 seconds. That is dramatically fast. We really want to improve it. No, that's pretty quick. But the truth is, though, is that we're only dealing with 100 sample sites. If I crank it up to, say, 1600, let's see how bad it gets. And so, oh wait, I need to actually run all this. Here we go. Evaluate that. And here we go. When I go from just 100 points to 1600 points, we see now we've gone from, what was it, a little bit ago, 0.04 seconds, and we see over 100-fold increase in how long it takes to do this. And so that's a lot of time, and if our problems get larger and larger, we have maybe bigger regions where we're trying to find approximations and things like that, it's going to slow us down dramatically. And so we want to make it better. And so that's what this whole lesson is about. So what we're going to do is we're going to make a gram matrix, and this gram matrix is going to be made from all of our exponentials, from our Gaussian. So we're going to have the exponential of -1/mu times the gram matrix that we get from, just say, xi minus xj squared, and that's what we're going to do, right? But we need a matrix that is going to be xi squared. This obviously isn't code, but I'm just showing you roughly what we're doing. So 2xi transpose times xj plus xj quantity squared. Okay, and so in where I put all these xi's and xj's is where we're going to have to actually put the real matrices. So I know that this guy is actually just going to be h prime times h, because h, if you take a look, is a whole bunch of, it's basically 2 rows, and each column is going to be our 2-dimensional data site or sample site. So there you go. This is all the pairwise inner products between them, but now I need to figure out how to do this. So let's go ahead and take a look at what we get when I say diagonal of h prime times h. And it is just a column. Or it is just a column vector. And let's see what let's take down the number of samples just so it looks better. Let's put it down to 10. And so, right, so now if I take diagonal of h prime times h, it should only have 10 sites. And so yeah, so there you go. And this came directly from the column here. So the first entry was 0.3611, and the last one is 0.2348. And if I take a look, the last entry of this matrix is 0.2348, and the top one here. So you see that it really just extracted these diagonals. Okay, so that's what we got. I am going to take the diagonal, I'm going to take a prime so that I transpose it, and so that becomes a row. And I never remember exactly how to do this, but let's see. So I'm going to do rep mat, and just to start I'm going to say 2 and I'm going to say 1 here. So we're going to basically repeat this matrix, and we're going to have 2 rows out of it if I am doing it right. There we go. So see, that was the first entry and that was the last entry, and it's been repeated twice. And so what I really want is I want this to be a square matrix. So I'm going to say rep mat, and I'm going to say I'm going to make it how many samples, because that is the size of h, right? And so then that is going to be my rows. So I can go ahead and I can throw that into my gram matrix. Boom, there. And then I can do that same thing again, but I'm going to take its transpose. And so just to make the code a little bit more readable, so ... here, and ... here. Okay, so keep everything in one spot. All right, so this is going to take care of all my all of our norms of the vectors down the rows, and this makes it norms of the vectors down to columns. And so that should actually be all we need. And so I think that is coded. So let's go ahead and run the code up to this gram matrix, just to make sure everything's in there properly. And I'm going to change it from being 10 to 1600 again. And so let's go ahead and run that. Evaluate and give it a bit. Should take about 4 seconds. And boop, there we go, 4.7 seconds to do that gram matrix. And that's a lot. I mean, who's doing interpolation at this point? I mean, you have pretty much as many samples and sites as you need. I mean, that's incredible. All right, it's like swarming with ants. I guess you didn't see that. All right, hold on. Let me just run it again. Another 4 seconds won't cost as much. Anyway, so boom. No, boom, boom. Still working. There we go. Oh no, it ran the whole code. I didn't want that. All right, there we go. So there we go. And so that is an incredible number of points, like I said, crawling with ants. All right, but so how long did that take? Again, it was 4.37 seconds. And if I go ahead and I try to run this, let's see what we get. It's going to take, here. When you do everything live recorded, I mean, it's all these little embarrassing bits don't get edited out. So let's delete that. And let's just go run this. Oh, evaluate that. All right, 0.03 seconds. And so that is coming down from over 4 seconds. And so that is more than a 100-fold increase or increase in our speed. And so now, just to make sure we're not crazy, let's take these two and let's compare them. So we're going to compute the regular gram matrix through the double for loop, and then we're going to compute the gram matrix with the other one. And again, we can see a fantastic increase in time. But let's take a look at the maximum of the absolute value of the difference. So we can see exactly how good we got. And I might be embarrassed and have something more than just a rounding error, but nope. That's what it is. So it is down to 10 to the minus 15, and that just comes down to computational storage, the order that you take, you know, arithmetical operations and things like that. And so there's rounding errors that happen throughout there, and you're never going to really do much better than that. So that is basically 0. Okay, so we can kill this, and now our code runs faster. Okay, so that is one spot, but there's one other place that we need to improve it, and it is here. We saw last time that we were able to take our weights and multiply by a bunch of other things. And so if we want to say do tick and talk here again, and there are better ways of timing things, but this works fine. So if I go ahead and run this, let's give it a second. 16 seconds. That is a lot of time. So we would like to be able to improve it, and one way to improve it is to eliminate this for loop. So let's go ahead and see if we can do that. So what we need is we need our z approximation at ij to be equal to the exponential of negative 1 over mu times something. So again, we need to so again, what we're going to be doing is we're going to be taking our rep map from our samples here, and then we're going to have h prime times h, but that's not quite everything. Actually, hold on, let me actually write out what we need. So we're going to have h. Okay, so what we're going to have is we're going to have our kernel function xij so we're going to have, say, xy minus h, and x and y are fixed, and so that's going to stay the same each time all the way down, and h is going to change as we go through each row. So what we need is we need the diagonal of h. That's going to stay throughout here. And so this needs to be a column. And so that goes there. And then we're going to subtract twice of keeping h's on the left, make sure that it stays as rows, so it becomes h prime times our xij semicolon yij, and then we're going to add the norm of this guy, so we're going to have this transposed times this. All right. Now this is actually just going to be a scalar, but what happens in MATLAB is that if you add a scalar to a matrix, it adds it entry-wise, so that should be fine. So exponential of minus 1 over mu. I hear my children going, so it's causing me anxiety before screaming starts happening and children start running around. Anyway, so there we go. And so that should end up working out. So I think, unless I made a mistake, that should be fine. Let's try this again. Oh, made a mistake. All right, so invalid expression, calling or indexing. Yeah, there's my kids. Okay. All right, too many, not enough. Here we go. There, okay. And boom. All right, so 1 is 1 by 1. Oh, right, z approximation ij. Oh man, forgot to hit it by weights. Okay, so this is a vector of my evaluations of my kernels, and this is the weights that need to be hit against them. The weights themselves, I think, is a column vector, so that should be weights prime, and so then this will perform the sum. All right, so that should all work out. Let's go ahead and evaluate this. So I hit a little road bump there in my description. So before we saw that this bit of code actually took about 16 seconds or so to run, and we would like to vectorize it. Now before I just vectorized the inside and it worked out, but this time it didn't, and actually made it take longer. So I vectorized the entire block here, and the way I did that is I took my evaluation sites, just where we're going to plot the function, and I threw them into, took those 2x2 arrays that came out of mesh grid, and I turned it into a single column. Then I took those y's and I turned that into a single column as well, and I put them side by side, and that gave me row vectors, and I transpose that so I get column vectors just the way I like. Now, in order to make everything work, you're going to basically have as many rows as you do of your sample sites and as many columns as you do for your evaluation sites. And then what we're going to do is we're going to multiply by weights and weights prime. And so when you do that, it's just basically going to take the dot product between your weights and every single column. And so every single column is all of your kernel functions evaluated at those particular evaluation sites. So how do we do this? So we want to make sure that we have as many rows as we do sample sites. So we take, and this guy is going to represent that vector squared from our site, and so that goes here, and I want to take that column and I want to repeat it as many times as I have evaluation sites, and so this just basically gives me the size of those evaluation sites. Here, this is just what we have been doing this whole time. We take h prime and we multiply it by big eval, and so then that's just going to basically take that middle, make that middle portion, and this really is what governs the entire size of the overall matrix. And then for the last bit, we want to repeat this guy over and over again. So this is our inner products of the evaluation vectors against themselves, and so that ends up being squared. And so then we want to repeat that over every single column, row, or every single column. Right, so this determines this is one big row vector because I could put a prime on it, and now we copy it down the rows, and so we make as many copies as go into how many samples, and then we only want one copy in that other direction. And once you do that, so the other one took about 16 seconds, and this code here is done already. Now here what we do is we use a reshape command in order to get everything back. So I stretched all these guys from a two-dimensional array down to a single column. And so what I want is I want to go from that single column down to a two-dimensional array, and so then that's what I do here. And so we know that one side length should be the length of the evaluation vector that we started with way at the top in the plot, like maybe 3 lectures ago. And then here this just says make the other dimension whatever size you need to. And if I do that, let me just go ahead and kill this. And let's go ahead and bring up some plots. Let's see, let's go run the code. And so there we go. The entire thing runs really quickly. And so we have figure 1 here. That was super fast. And I have an error in my code for some reason. And so let's see what happens if I run this. All right, so that part worked. And so there we go. And let's see, last one, our approximation threw an error. Oh, I don't know where the error came from, but it seems to have gone away. And so there we go, 10 to the minus 3. And that's because we have a crap ton of evaluation points. Although, all considering, at 1600 point, oh, that's 200. Yeah, okay, so this is great. And now let's see if we can scale it up. And what was this anyway? we had some sort of error matching and number of columns, samples. I don't know. But let's see. Maybe it's not going to cause a problem again. 1600. Boom. All right, so everything super fast again. And so this was with 1600 points and the speed was roughly the same. And so here we go. That's our 1600 sample points. And if I show you my second figure, and this is our approximation, looking pretty snazzy. And yeah, worked out pretty good. And so the whole thing was super fast. And yeah, can't ask for anything better. Let's see. Let's run it again just for hell of it. Boom, whole thing ran fast. Okay, yeah, so it's working. There you go. Code for the Gaussian RBF that is really snappy and really fast. So that's good. And next time we're going to jump into the symbolic toolbox to take a look at a few other radial basis functions, and we're going to take a look at making the the Wendland RBFs. And so those are compactly supported RBFs that have a Hilbert space that is norm equivalent to Sobolev spaces. And so yeah, that's gonna be really interesting. Anyway, so hang in there and subscribe, and yeah, I'll see you next time.